Okay, so this is another question. Okay, and it's to do with it's non-linear. Okay, so we've got to use energy methods to solve it. So I'm just going to run through this question very briefly. It's quite straightforward, this one. There's no force being applied, which helps. We've got two variables, x and theta. And so the first step is to work out what t is, and the second step is to work out what v is. T is going to be the kinetic energy of the trolley plus the kinetic energy of the pendulum. Now, to work out the kinetic energy of the pendulum, we need to know its velocity, so let's do that first. Coordinates of the pendulum, xb being the bob at the bottom of the pendulum, and yb, so this is the position. We have x plus, and then it's obviously this distance here, which is L sine of theta. Okay, so it's this distance from here to here, which is x, and then from here to here, which is L sine theta. And then the y position, obviously, y is upwards from this datum point here, so we've got minus L, and then obviously it's this distance here, which is cosine of theta. Now, to get the velocity, x dot b and y dot b, we have to take the time derivative of this term. Okay? So the time derivative of x, we've got obviously x dot, and then plus L theta dot cosine of theta. Okay? Now that's obviously using the chain rule, because you have to take, obviously sine of theta turns into cosine of theta, but you have to take the derivative of theta out as well. And then here, cosine turns into minus sine, so the minus sign disappears. We have L theta dot sine of theta. So T is 1/2 big M x squared, x dot squared, plus 1/2 little m x b dot squared, plus 1/2 little m y b dot squared. Does everybody agree? One-half mv squared for the trolley, 1/2 mv squared for the bob of the pendulum in the x direction, and 1/2 mv squared for the bob in the y direction. If you add all those up, you're going to get the kinetic energy of the system. So there's a bit of manipulation we need to undergo here. So T plus 2 x dot L theta dot cosine of theta. So that bit there is x dot b squared, okay? So I've taken this term and I've squared it. So you have to multiply it out. It's 3 terms, okay? And then this term I just have to square. So plus L squared theta dot squared sine squared theta. I took the 1/2 m outside of both of those terms. So I've just rewritten it, grouping things together, and I've grouped together cosine squared plus sine squared. Why have I done that? So it's just rewritten the line down. This line is just rewriting this line, but I've grouped together cosine squared and sine squared. And the reason I've done that, obviously, is this value is 1. And so combining things together, we've got t is 1/2 big M plus little m x dot squared plus m x dot L theta dot cosine of theta. So the 1/2 m has come in here. Half times by 2 is 1, and m times by this bit. And then plus 1/2 m L squared theta dot squared. There is t. We've got the spring kinetic energy, kx squared, and then we've got the gravitational potential energy of the pendulum. So that's minus, because obviously it's, but then we take this value for y here, mg times by that. So minus mg L cosine of theta. So here's our y position, and obviously mgh is gravitational potential energy. And so mg times by this gives us minus mgl cosine theta. So if the potential energy related to the spring and the potential energy related to the gravity in the pendulum, okay? There's our V. So that's step 1. Step 2, or no, the end of step 1 is L, which is T minus V. So I'm going to write it out. So I'm going to say Q1 is x1 is x and Q2 is theta. Big Q1 is 0 and big Q2 is 0. So for Q1 we need to find dl over dx dot. So to do that you take L and you look for every term with x dot in. So you've got this term. The derivative of that would be just big M plus little m x dot. This term has got an x dot in, and so it's just a part of that term, so we obviously it just disappears. Okay, and neither of these terms have x dot in. Lovely. You then have to take the time derivative of this. So d by dt of dl over dx dot. Well, this one just becomes m plus m x double dot. And with this term, this term, there's two values in that term that will change with time. One is theta dot and the other one is theta. And so we have to use a couple of rules, differentiation rules here. If you remember back in high school maths, dx times by y dt, assuming x and y vary with time, this is going to be dx dt times by y plus dy dt times by x. Okay, so that's what we're going to use here. And obviously, if theta dot is x and cosine of theta is y, when you're doing dy by dt, you've also got to use the chain rule, because it's a function of y, or function of theta. Okay, so we have, we've got m, l, theta, double dot. So that's the dx by dt, cosine of theta. Okay, plus m, l, theta dot squared, sine of theta. Sorry, there's a minus sign there. That should be a minus sign, apologies, because obviously the differential of cosine is minus sine. Okay, so that's minus sign. You've got those two terms. So like I said, you have the chain rule, so a theta dot comes out, which makes a theta dot there, times by theta dot gives you theta dot squared. So that's the first term. The second term, dl over dx, well that's quite straightforward. There's only one term in the Lagrangian that has x in on its own. There's this one here. So that's just kx, minus kx. Is there a question? No? So that's the Lagrange's equation, and so we can stick this in here now. We have sorry. Is that low down enough? What I'm going to do is I'm going to fold this bottom bit under so we can still see L. Okay? Everybody got it down? With the pen. Right, so now we have to deal with I is 2, so that's dealing with theta, and so we've got dl over d theta dot. So any term with a theta dot in, we need to take into account. So this term is disregarded. This term, we've got a theta dot in there, so obviously this is just going to be m x dot l cosine of theta. Here we've got a theta dot term as well, so that's plus m l squared theta dot, and that's it. We have to take the time derivative of this, d by dt. And so this is, again, this is a case where x dot is going to change with time and theta is going to change with time. So again, we have to use the multiplication rule. So this is going to be m x double dot L cosine of theta plus m x dot theta dot L sine of theta. Again, I've made the mistake, that's supposed to be a minus there. And then here it just becomes plus m L squared theta double dot. So again, that's a minus sign between those signs because the differential of cosine is minus sine. I need to think about that when I start writing the operator. So that's the first term. So the second term, we need to look at L and take all the terms that have a theta in without the dot in, okay? A theta in on its own. So we've got this term because there's a cosine theta there, and we've got this term because there's a theta there as well. So we need to take the integral of that, sorry, differential of that is going to be m minus m, I remembered this time, x dot, what is it? L theta dot sine of theta. And then over here, again, the plus turns into a minus, minus m g L sine of theta. So again, we apply the Lagrange's equation, which is this term minus this term. So we have m x double dot L cosine of theta minus m x double dot theta L sine of theta plus m L squared theta double dot plus m x double dot, x dot L theta dot sine of theta plus m g L sine of theta equals 0. There's two terms in here, one's a plus, one's a minus, they're the same. They disappear. And so we end up with m x double dot L cosine of theta plus m L squared theta double dot plus m g L sine of theta equals 0. Thank you very much. There we go. So those two terms are identical, so we can just delete them. They disappear, and we end up with just those three terms for the motion of theta. So there's the equation for x, and there's the equation for theta, equations of the motion. And notice they're very coupled. And next week, I'm going to revisit this problem, and we'll find out what happens when you assume small angles, and it's quite nice what happens when you assume small angles.